to talk about a newly discovered particle in elementary particle physics named as X17. Now, the discovery of this particle actually was first reported in 2016 by a Hungarian group working from an institute called Institute of Nuclear Physics, also called as ATOMKI. They had earlier reported, based on their experiments on radioactive beryllium nuclei, that they observed deviations of angles between emitted electron-positron pair is way more than what is expected, and therefore there must be another unknown particle involved in these experiments, which they termed as X17. Now in 2019, the same group has reported similar results involving helium nuclei, which when excited through bombardment of energetic proton beams goes to higher energy states, and then during de-excitation from one of the higher energy states to a lower energy state results in emission of again electron-positron pair, but the angle between the emitted electron-positron pair is way too high. In the case of beryllium, the angle at which the electron-positron pair for high energies was about 140 degrees, whereas in the case of the helium, this angle has been reported to be about 115 degrees, still high, still inexplicable in terms of the standard known theories in physics. Therefore, they explain the results based on assumption that another particle, which they call as X17, must be involved in these radioactive decays. For example, beryllium, when gets excited, is very unstable and it de-excites and becomes de-excited beryllium along with the emission of this X17 particle. Of course, this X17 particle further gives rise to emission of an electron-positron pair, because essentially the de-excitation occurs along with emission of what is called high energetic gamma ray photon, and then this dissociates into an electron-positron pair. Now, what has really caused up a lot of stir in the world of physics is, way back in 2016, when the group reported these results, there was a lot of skepticism, and there was a lot of call for subjecting these results and experiments to great scrutiny, because this group, the Hungarian group, has been notoriously involved in similar reports earlier, at least 3 times, and in all the earlier 3 occasions, the results have not been able to verify. We have not been able to verify scientifically those results, and therefore they have been discarded. So when they report this time around a similar discovery, the scientific world has taken it with a lot of, not a pinch of salt, but a lot of salt, so to say. Therefore, the repeat of the same experiment on another system, earlier it was beryllium and now it is helium, indicating again to the presence of probably a yet to be discovered particle, has really again created a lot of hype in the world of elementary particle physics. Now, standard elementary particle physics research involves high energy accelerators, which are high energy particle accelerators, such as the one in CERN. CERN is a very popular institute in Europe carrying out such research, and they have what is called a Large Hadron Collider, which is a high energy particle accelerator, shortly called as the LHC, which discovered in 2012 an earlier theoretically predicted particle called the Higgs boson, or the God's particle. Now, the Hungarian group, on the other hand, has not used, they have not used anything on such massive energy scales, because these involves a lot of energy, and the energy scales here are way higher than what energies that have been used by this group now. In these experiments, actually comparatively slower proton beams are used to bombard these nuclei, and the excitation takes place because of that, and the de-excitation results in emission of such particles. Now, the standard model has been verified many times, because the standard model has led to discovery of a lot of particles and new elementary particles, and the standard model involves fundamentally in particle physics only three forces, namely the electromagnetic force, the strong nuclear force, and the weak nuclear force. Now, interaction between any matter in the universe can be explained via these three forces, and the fourth well-known force is of course the gravitational force, which is not strictly accommodated in the standard model of particle physics. But Einstein's general theory of relativity has sufficiently explained the involvement of gravitational force between massive objects, and therefore particle is involved in the exchange of gravitational force between objects, and such particles are called gravitons. In the case of electromagnetic force, the particles involved are photons or light. These are the particles that are involved when an electron interacts, for example, with, let's say, a proton. Both are charged objects and they interact via the electromagnetic force, and therefore photons are exchanged in this interaction. For the strong nuclear force, it is the gluons that are exchanged, whereas for the weak nuclear force, it is what is called the vector bosons, such as W and Z bosons, that are involved in the interaction of two nucleons, for example, via the weak nuclear force. Whereas the case with gravitational force is the yet to be proved gravitons, which are also considered to be bosons. So all these particles that are exchanged in such interactions of known fundamental forces, they are all bosons. Photon is a boson, gluons, as well as the W and Z bosons, as well as the gravitons, all these objects are basically bosons. Bosons are fundamental particles that have integral spin. That is, their spin can be either 0 or integer numbers. Whereas particles like the electrons, the protons, and the neutrons, they are half integral spin particles, and therefore they are classified as fermions. These are nothing but bosons. Now, therefore, the standard model should be able to explain the results obtained in these two experiments carried out by the Hungarian group, and it should be able to explain the deviation of such an angle at high energies between the emitted pair of electron and positron. but it is not possible to explain these results using the standard model. Therefore, the groups speculated that another unknown particle might be involved in this reaction, and they termed it as X17 because X is something that is unknown always. We use the alphabet X, and 17 signifies the mass of such a particle. If at all such a particle exists, it should have a mass of about, the rest mass of such a particle should be about 17 MeV by c square. We know the units in elementary particle physics for objects, mass units for example, is MeV by c square. C is the velocity of light, M indicates million or mega, electron volt, EV is for electron volt. So this mass for this object is about 34 times the mass of electron, because the rest mass of electron in terms of MeV over c squared units is 0.5. Therefore, this boson that could be involved, this is a boson by the way, and the boson that could be involved in an yet to be discovered interaction has a mass that is about 34 times the mass of the electron, and still this is considered to be a lightweight boson. And if at all such a particle exists, and if at all there is an interaction that is yet to be understood, that could lead to what is called the fifth force of nature, which is unknown, which is yet to be proven. Therefore, this discovery and the recent report of the same group has created a lot of stir in the world of physics, and it has been taken with a lot of skepticism. A lot of criticism has come out for their results and data and the way they have analyzed the data. So it hasn't been peer reviewed, it has not been accepted in any standard peer reviewed international physics journals, but it has been uploaded rather to the repository of articles called ATOMKI, and it will be subjected to peer review and a lot of scrutiny, both in the archive and in whatever journal they submit this research work to. Whereas the earlier work was published in a prestigious physics journal called the Physical Review Letters. So this result, the original result, has been confirmed by the same group, but it has not been verified and confirmed by any other independent group. So no other independent group has been able to confirm the results, and therefore this is still a lot of speculation. If at all this is true, this could change the way we do physics, because this kind of could lead to discovery of a new force of nature, and this particle, if at all present, could also be considered to be a boson that is exchanged when two objects in this universe interact via this unknown force. And therefore there is also speculation that this could lead to the explanation of what is called dark matter and dark energy in the universe, because about 86% of this universe is made up of dark matter and dark energy. And if at all there is a fifth force involved, and in the interaction via this fifth force, if at all these X17 particles are exchanged, then this could be the way the dark matter interacts. That is, two dark matter particles could probably be interacting via this force by exchanging these particles called the X17 particles. But right now it is nothing more than a scientific speculation, though it has created a lot of hype. Let us keep our fingers crossed and hope that this turns out to be true this time for the Hungarian group, and this leads to kind of fundamentally new understanding of not only particle physics, the whole subject of physics as well. Thank you.